Hello everyone, this is lecture 7 of course BE544. In today's lecture, we are going to deal with image classification using histopathology patches. If you remember, classification is used to identify a category or a class to which an object is an image belongs. So we have an image and we are going to apply that image to a specific system or a model, so that image can be recognized to a specific class. There are different approaches that can be utilized for classification. One of them is CNN or Convolutional Neural Networks. They consist of a set of layers that are cascaded together that can accept the input and produce a category or a class as an output. These CNNs can be designed manually. You can design your own CNN by stacking and cascade a set of layers together with a specific criteria that meets your problem. Or you can use a pre-trained model in some approach that's called transfer learning. And basically, transfer learning means that a model is designed and trained on a specific dataset, and then the weights or the optimized weights for that model are stored in a file. Then you can use the learned knowledge from that model and refine it or fine-tune it for your dataset, such as breast cancer histopathology dataset, to produce the target output depending on the categories or classes in this dataset. There is another approach called vision transformers, and that approach uses a different criteria of a design that we are going to demonstrate it in a future lecture, which is simply divide an image to a smaller batches and embed them into numerical vectors with positions, and then encode that to produce the output at the last layer. One more approach is called You Only Look Once or YOLO, and that approach is mainly produced to make detection and localization, but some models from YOLO, such as YOLO version 8, can be modified to be used in classification. And last, you can mix multiple models together or stack them together, such as you can combine between a pre-trained model and vision transformer, or combine between YOLO and vision transformer. And by combining any two approaches together or stacking two approaches together, you can call them a hybrid design. So the main idea is we have some images that we need a model to train on them, and then after training and learning we need to produce an output. So you can assume that model as a black box that takes an image and produces a label or a category. In the following lectures, we will deal with these designs starting from CNNs, vision transformers, and ending with hybrid designs, and understand how each of them can work and can be modified and utilized for your problem. For example, what we used the BACH dataset. So let's start with the CNN. So a CNN, or a convolutional neural network, is a type of artificial neural network which is designed specifically to analyze structured grids such as images and videos. And a grid here means you have a 2D dataset or a 3D dataset. A 2D dataset such as images and 3D dataset such as videos. So simply, CNN work by applying filters on the input data, and these filters will be able to extract the different patterns and features from the images. And the uniqueness here in these filters is that they are capable to be adjusted during the training process and be fine-tuned for your dataset. So you have an initial filter or a kernel or a block which is fine-tuned based on the input data during the learning process. So by doing that, automatically during the training process, this will eliminate the necessity for manually crafting filters in CNN. And by that, this will enhance the flexibility in both the quantity and relevance of filters applied to a specific dataset. Commonly, CNNs are trained using large datasets, and the learning process can be split in two directions, forward and backward. The forward, some values are calculated, and backward, the update of the weights or the update of the parameters of the filters or the CNN is done in something called backpropagation. In backpropagation, the network learns to adjust the weights of its filters and fully connected layers to minimize the difference between the prediction and the ground truth labels of the training data. And this means you are training a model that produces a prediction. So the aim of backpropagation, you are trying to minimize the error between that prediction and the actual label, which is, for example, you are giving a benign image and the prediction is, for example, benign. So the error here will be the difference between the predicted benign value and the actual benign value, which will be in that case 0. But if there is another value, such as carcinoma, then there is a difference between the value of carcinoma as a prediction and the actual, which is benign. So the model will try to minimize that error, aiming to refine that prediction to be correct. CNNs differ from regular neural networks in their utilization of something called convolutions to perform mathematical operations. So instead of using matrices like in traditional neural networks, you are using convolutions, and we are going to understand after a bit how convolution is working. So as we need to design a convolution neural network, we need to know the structure of the different layers that can be cascaded together to construct that CNN. It starts by an input layer. So the input layer here in a CNN receives the raw data, and the raw data here is represented by multiple dimensional array. As mentioned, 2D for images and 3D for videos or volumes. And simply, an image also can be represented as a 3D. Why? Because an image is read in RGB or 3 channels, so we can assume that an image is a 3D component because it consists of a channel or an array for R, an array for G, an array for P, RGB, and the dimensions of it can be height, width, and 3 for the RGB channels. So we have 3 values, so we have a 3D matrix. After setting an input layer, we need to construct a set of convolutional layers after that, and as mentioned, these layers have filters which are learned to extract the patterns. And by utilizing these layers, we are applying convolutional operations. So this is an operation that slides over that filter and get an output. So assume we have a filter like that, and we have a convolutional matrix like that. That matrix will slide over the filter and produce something called feature map. So simply, that matrix will be multiplied by that region and produce a value, and then slide to the right to that region and produce another output, and so on for the rest of the image. So by getting a value for each multiplication done here, we can get another matrix with specific dimensions, and this matrix or this output matrix between the multiplication between them is called a feature map. So each filter in that layer is used to detect specific patterns or features. So by increasing the number of filters in that layer, this means you are telling that layer to capture different patterns for each filter, because each filter is learned individually. So if you have, for example, 8 filters, so in that case, each filter will be individually learned from the other 7 filters. After each convolutional layer, we need to apply a function called activation function. And that activation function will help to introduce nonlinearity in the network. And by introducing nonlinearity in the network, this will let the network learn the complex relationships between features. So instead of the multiplication and getting a linear function, by applying the activation function to the output of the convolutional layer, some sort of nonlinearity can be introduced. And why do we need to introduce the nonlinearity? Because if you assume if you have records like that or data like that, you will need to make some sort of nonlinearity in your learned curve or the curve, so it can capture most of the data and reduce the error. So in CNN, as we are dealing with images, the relationships between the features are more complex. So we need to add the activation function to introduce that nonlinearity to let the layer be able to capture these complex relationships. After the activation function, a pooling layer can be introduced. And the aim of that layer is to downsample the feature map produced the convolutional layer and the output of the activation function, and this will reduce the spatial dimensions while retaining the important features or information. So as a scenario, you have an input applied to a convolutional layer which extracts the patterns and applied to activation function to produce some sort of nonlinearity, and the aim at the last layer to produce a specific class. So you need to apply the pooling layer to let the architecture or the model be reduced in size until it reaches that category or that class. So instead of dealing with 512 by 512 by 3 images, you are trying to reduce that size cascadely until we reach that category. So if you visualize it, you have a large image and you need to reduce the image in size or the feature maps in size until you reach the category. So that is the rule of pooling layer. It reduces the spatial dimensions, but the most important thing here is that they retain the important features. There are different types of pooling layers, but one of the most common used pooling layers is called max pooling. And max pooling here, from its name, it tries to find the maximum value of a specific region. So as we saw in the convolutional layer, we have an input and you have a convolutional matrix which slides here and it gets a feature map. The same approach is done by the pooling layer. There is a window that will apply it on the output, and for each region it will extract the maximum number. So for example, if we got that region, we need to find the maximum number and produce it. For that region, we will find another maximum number and produce it. And by continuing that operation, we can obtain another output with the most important features or information, but in a reduced size. Another type is called average pooling, and average pooling here calculates the average, not the maximum, of the window. So if you are here, you need to calculate the average value between all of them. So pooling helps reduce the computational complexity and prevent overfitting by focusing on the most important features. You can apply a set of convolutional layers with a cascaded pooling layers until a certain point that you will apply after that something called flattening. And the flattening here, you are going to convert the feature maps, which are in any dimensions such as 2D or 3D, into a one-dimensional vector. So you are converting from the spatial informations to a format which will be suitable for the following layers to be able to produce a category or a class as a single value or a single vector. So flattening is done by concatenating the dimensions together. So this layer or this step is important, as mentioned, for the following layers, which are called fully connected layers. And fully connected layers are commonly used in artificial neural network, and they consist of neurons which are arranged in a fully connected manner, where each neuron in the following layer is connected to every neuron in the previous layer. So the aim of the fully connected layers is to convert and map and apply transformations from the flattened feature map to get the desired output. Fully connected layers, or in short FEC layers, capture high-level abstractions and relationships between features learned in the earlier layers. As we build the model, we need to learn it. So we need to introduce something called loss function. So a loss function will be able to measure the discrepancy between the predicted outputs and ground truth labels that will be used later for backpropagation to update the weights and parameters for the different kernels or filters. There are many loss functions that can be used, and it depends mainly on the task you are targeting. So for example, cross entropy loss function can be used for classification, and mean squared error can be used for regression tasks. To apply backpropagation, we need a formula that uses the value of the loss function or the error to update the different weights and biases. So this happens in the parameters optimization. In parameter optimization, you are using an algorithm to adjust the weights and biases of the network in the direction that minimizes the loss function. There are many optimization algorithms such as stochastic gradient descent, or in short SGD, ADAM, and root mean square or RMS prop. Each of them have something called learning rate. If you saw the formula for each optimizer, you will find some factors that can be modified or updated. One of them is the learning rate. The learning rate controls the size of parameter updates, and we can assume that learning rate is a critical hyperparameter that affects the optimization process. So as you see, there are two terminologies, parameters and hyperparameters. What is the difference between them? Parameter means the weights and biases in a network, and this is updated during the learning process using an optimizer and the value of the loss function, while hyperparameters are the configurations of the network, such as the learning rate, number of layers, type of the optimizer, which optimizer will be used. These are the configurations, and tuning or updating the hyperparameters requires a separate algorithm for tuning. So if you need to optimize both of them together, you are selecting an algorithm for hyperparameter tuning, for example, random tuning. So you will have a set of configurations, and for each configuration, you are selecting a random value. For example, you are selecting from the scope of learning rate a value of 0.5, and from the optimizers ADAM, for example, and you are using these two values to learn the model from scratch and produce a measure, for example, accuracy. So in that case, assume you are getting 0.8 for ADAM and a learning rate of 0.5. Then you are getting another couple of values, for example 0.6 and SGD, and relearn again the model from scratch on the same dataset and produce the value as a measure, for example 0.9. So we have two separate trains, and by applying that on many different configurations, the aim is to maximize the performance. So you can finalize by saying, I will use 0.6 with SGD for that dataset. So in that case, you are tuning the hyperparameters. But for the parameters, the tuning is done internally during the training process in something called backpropagation. So backpropagation involves computing the gradients of the loss function with respect to the network's parameters and then adjusts the parameters accordingly. This process will continue until convergence, and convergence here simply means you are getting the same output or the same loss for multiple times, or you are approximating the target value, which is 0, because our aim to get a loss value of 0, there is no loss. So if you are approximating that 0 with a small difference, this can be also called convergence. Or simply, you can train your model for a set of iterations. You can say, I'm just training that model for 1000 iterations, whether it converges or not. After training, you need to apply evaluation. So you are evaluating your model after training using a separate validation and a test dataset. So to distinguish between training, validation, and testing, simply, as we said, we are going to train the model for 1000 iterations. So what are the type of dataset that will be used in the learning process is called training. After each iteration, you need to calculate a score of how generalizable that model can predict. So you are applying the validation subset after each iteration and compute that measure. So if you have 1000 iterations, the training and validation will be used 1000 times. But after training and completing the training and evaluation process, you need to check the generalizability of the trained model at last on another and non-seen data, which is called test dataset or test subset. The measure we are getting is called performance metrics. Performance metrics are too many, and each can be used for a specific task, and many of them are general for all tasks. But for classification, the common performance metrics are accuracy, precision, recall, and by getting these metrics together, we can get insights on how the model performs on each category or each class. And as mentioned, hyperparameter tuning involves experimenting with different combinations of hyperparameters to find the optimal configurations that maximizes the model's performance on the validation or testing dataset. After completing that whole process, we need to store the model for testing and future use, because the learning process can take time. For example, it can take from hours to days or to months. So it's not reasonable to train the model every time to get a single output. So you are training a model and then you have to store it after tuning the hyperparameters and the parameters. So you are storing the architecture, which is a design, and parameters such as weights and biases in a suitable file depending on which package or which library you are using to be used later interface on new data. In the next few slides, we are going to understand more about each layer. So let's start. We started by getting an input layer that accepts the raw data, such as images or videos, and then they are presented to a convolutional layer, and as said, it's the core of building block of a CNN, and it performs the convolution operation, which is the fundamental operation in image processing and computer vision tasks. So the aim, as mentioned for that layer, is to extract patterns and features through the learnable filters or kernels. So a filter or a kernel is a small matrix n by n or n by m, depending on the configuration you are setting for that kernel or filter, and each filter captures a specific pattern or feature. These features can be edges, texture, or shapes in an image. So instead of extracting them manually, the filters will do that for you. There are common filter sizes such as 3x3 or 5x5, and you can also include that size as an hyperparameter to be tuned. That filter or kernel with that small size slides using the convolution operation. So there is a dot product that occurs between the filter or the kernel and the input data, or the previous map or feature map, or the previous matrix. And based on the dot product that happens between the filter and a portion from the previous layer, there is a single value that comes. And by cascading and putting that single values in their places, we are getting the feature map. And sometimes the size of the output feature map may be smaller than the input due to the border effects. So padding is introduced in that case. So padding can be added to the input data to ensure that the output feature map has the same spatial dimension as the input. So instead of using 512 by 512 input data, you can pad the boundaries of it with values. So it can, for example, become 520 by 520. It depends on the configurations and target output feature map and the size of it. You can handle the padding. There are common padding techniques such as zero padding, where you are adding zeros around the boundaries, and you can also apply valid padding where no padding is added. There is a factor called a stride, and stride here determines the step size at which the filter slides across the input data. A large stride reduces the spatial dimensions of the output feature map, while a smaller stride preserves more spatial information. So you need to select a mid value between both of them that can enhance and increase the performance. So you can assume a stride is a hyperparameter that influences the spatial resolution of the feature maps. As said, each filter produces a feature map which is an n dimension. It can be 2-dimensional array, and the more filters you are applying, the more features you are getting. Then you are finalizing that layer by applying an activation function, and activation function is an element-wise operation. This means that each element in the feature map has an activation function. So if you are applying on a feature map of 100 by 100, you are applying the activation function on each element. This means the activation function will be applied 100 square times. There are many activation functions such as rectified linear unit or ReLU, and commonly activation function introduces the nonlinearity to the network or the feature map. Specifically talking about ReLU, it replaces negative values with zeros. So if you have any negative values in the feature map, they will be converted to zero. The weights or parameters of the CNN or the convolutional layer are learnable parameters, and you need to distinguish between learnable parameters and non-learnable parameters. Learner parameters means they are being updated during the backpropagation process. So on each iteration, these learnable parameters or the weights and biases of the convolutional layer will be updated. Non-learnable parameters are fixed during the training process. So if you are going to initialize them with values, they will be kept as it is. You can also, in your code, specify a specific layer or a convolution layer to be non-trainable or non-learnable. Why can we do that? As mentioned from a bit, in transfer learning or using a pre-trained model to be refined or fine-tuned, you have already updated weights. So you can simply take the pre-trained model and fix a portion of it so that the weights of that portion will be non-learnable. So when you refine or fine-tune that model again, you will just update a small portion of the pre-trained model. So selecting between learnable and non-learnable parameters during the training process depends on the application and on what model you are going to use. The extracted features maps will be relevant to the task at hand. So if you are applying classification and learning histopathology batches, for example PACH dataset that we used, the features will be corresponding to the patterns in this dataset. So let's have an example. You have a 5x5 image and a 3x3 filter matrix. Let's stride for both directions as 2x2 and the padding as 0. This is the image matrix. This is the filter matrix. The image matrix is 5x5, 5 columns by 5 rows, and 3x3 filter. The filter matrix is 3 rows by 3 columns. And the stride means, as mentioned, what is the step size to move between an operation to another. And padding of 0, this means we will use the input as it is without being padded. So we will begin on the top left corner and cut a portion of 3x3 similar to the size of the filter matrix, and then perform dot product between each of them and sum the results into a single value. So for example, you will get 1 multiplied by 1, 2 multiplied by 0, and so on until you reach 2 multiplied by 1. And then you sum all of these values together, it will get 7. So the output feature map or matrix you put in that position 7. Then you move 2 steps to the right. So if you are here, then by 2 steps you will start from here to here. So you can obtain that matrix again and multiply it with the filter matrix, sum all of the values together, and get the corresponding output, which is 8, and put it in the corresponding place of the output matrix. Then after reaching the boundary, you will move to the bottom with a stride of 2 or 2 steps. Then you can reach that. After completing and calculating the output, you can reach that, and so on. What about if the padding is 1 instead of 0? This means you have the image as shown here, and you are applying padding around the boundaries with zeros. Padding is 1 means a layer of 1. If padding is 2, you are applying another layer. If padding is 3, you are applying 3 layers that surround the boundary with zeros. So after applying a padding of 1, as mentioned in the example, you will start to get the matrix, and then you make a stride of 2, then you get another matrix, and so on until you reach the end, which is here. So mathematically, how to determine the output shape of the feature map? You are given with a specific stride, padding, and filter matrix size alongside with the input size, and you need to calculate the output width and the output height so you can determine what is the shape of the feature map. So simply you are subtracting the input width by the filter width, and then add 2 multiplied by the padding and divide all of that by the stride. Then you will apply rounding. So if it's 4.8, it will become 4, 4.9 will become 4, 4.2 will become also 4, and then you add 1 to the output. So if you have an image of 15 by 20 and a 3 by 3 matrix for filtration or a kernel, and you are giving with a padding of 1, a stride of 2 by 2, what is the output shape? You simply substitute in that equation so you can determine that the output feature map shape is n by m. So the width is 15 minus 3 plus 2 multiplied by 1 divided by 2. So this will become 12, added to 2 will become 14, divided by 2 will become 7, plus 1 will become 8. We mentioned that activation functions are very important for the convolutional layers to introduce some nonlinearity on the feature map, so the model can learn complex relationships and nonlinear patterns. And if we didn't introduce that activation function, the filters will learn only and be limited to learn with the linear relationships between the features. So their ability to separate between nonlinear relationships and learn from them will be difficult. We mentioned ReLU as an example of the activation functions. We have many other activation functions such as sigmoid, tanh, or hyperbolic tan function, or ReLU, which is similar to ReLU function, but instead of setting all negative values with zeros, you are setting the negative values with a small value, which is a multiplied by z. We mentioned also that the pooling layers will cascade the convolutional layer, and they are used to perform downsampling on the feature maps, and their purpose to reduce the spatial dimensions and the complexity of the model, and they are important to avoid any overfitting that may arise. We mentioned that max pooling and average pooling are types of pooling layers or operations. So max pooling, importance here, it will preserve the most important features, while average pooling will reduce the impact of outliers and noise in the feature maps. And there is also something called global pooling, and the global pooling here aggregates the information across the entire feature map to produce only a single value for each feature map. So if you have n feature maps, you will get only n values or vector. And global pooling is commonly used in the final layers of the CNNs. So the difference between average pooling and global pooling: average pooling applies a window to each portion of the image or the feature map, and then slide to the right and to the bottom. So instead of n by m, it will reduce to n bar by m bar. But global pooling will get only a single value for that whole feature map. Similar to the convolution layer, there is also a sliding window in the pooling layer, and it moves from the left to the right and from the top to the bottom. So if you increased the window size of the pooling layer, you will get a greater downsampling. And if you decrease the window size, it will preserve more spatial information. And this also can be used as a hyperparameter. Together, convolutional and pooling layers will enable the CNN to learn the hierarchical representations of the input data, and this will capture both low-level and high-level features which are relevant to the task in hand. There are different benefits and advantages of pooling layers. First, as said, dimensionality reduction. So by downsampling the feature maps, pooling layers will reduce the number of parameters in the network, and this will lead to reduce the complexity and lead to faster computation and reduce the memory usage. Second, translation invariance. Pooling will help make the network more robust to small variations in the position of features. So this will improve the ability to generalize to unseen data. Third, feature localization. Pooling layers will retain important features while discarding irrelevant details. This will make the network focus on the most discriminative information for the task. For example, if you are dealing with histopathology patches classification, you are ignoring any irrelevant details in the patches and keep only and focus only on the features and information that discriminate between a category to another. For example, assume you have a 12 by 12 feature map and a 5 by 5 max pooling layer. So assume the stride for both directions is 2 by 2. So you are sliding to the right and to the bottom with a step size of 2. So to obtain the output from that feature map, you are getting 5 by 5 from the top left corner, and you are calculating the maximum value of that region. Assume you are using max pooling, you will get a value of 6 here. Then you step a value of 2 to the right, you will get that kernel or that region, and the maximum value in that region will be 9, and so on. Similar to the two formulas that calculate and determine the output shape of the feature map regarding the convolution layer, for the pooling layer, you are omitting the padding. So the equation will be the input width minus the padding width divided by the stride, and the height will be input height minus padding height divided by the stride. You then round these two numbers and add 1 to the output. So assume you have 25 by 20 feature map and a 3 by 3 max pooling layer. So with a stride of 2 by 2, what will be the output shape? Just substitute in the two formulas, you will get 25 minus 3 is 22, divided by 2 is 11, plus 1 will be 12. And for the height, 20 minus 3 will be 17, divided by 2 will be 8.5, rounded will be 8, plus 1 will be 9. After getting a set of cascaded convolutional and pooling layers together, you should finalize your CNN with a flattening layer that will convert from the n dimensions to a one-dimensional vector. And each element in that vector is called a neuron. And this will facilitate for the upcoming fully connected layers to work so that they can produce a category or a single value as an output. So if you have an input data with a three-dimensional array with dimensions height by width and depth or number of channel, by flattening it we'll get a one-dimensional array or a vector with dimensions of height multiplied by width multiplied by depth. So if you have, for example, 8 by 8 by 64, the one-dimensional vector will be the multiplication of these three values. It will become 4096 elements in that one-dimensional vector. Then you apply fully connected layers, and fully connected layers or FEC layers are also known as dense layers, where each layer in that fully connected consists of neurons, and each neuron is connected to all of the neurons in the previous layer. That's why it's called fully. The primary purpose of fully connected layers is to learn complex patterns and relationships in the input data by combining features extracted from the earlier layers, by doing an operation at each neuron, which is called a weighted sum of the inputs from the previous layer, followed by also an activation function. This will also introduce some nonlinearity relationships learning between the features. So activation functions are introduced in the fully connected neurons and in the convolutional layers. So this means that convolutional layers and fully connected layers contain learnable parameters, which are the weights and the biases, while pooling layers do not have any learnable parameters. Commonly, the last fully connected layer is called the output layer, and the size or shape or number of neurons in the output layer will depend mainly on the task you are targeting. So if you have 3 classes, you will get 3 neurons in the output layer. Each neuron reflects a class. So let's take a simple design example. You have an input here, and the authors in that study applied a convolutional layer, and then applied pooling layer, and then another convolutional layer, and another pooling layer, and then they flattened the output of the second pooling layer and applied a fully connected or a set of fully connected layers after flattening, and then they set the output layer, which is also fully connected, but the size of it depended on the problem in hand with them. So they only got 2 classes, tumor and non-tumor, so the output shape or the number of neurons in the output layer will be 2. So how to program and cascade these layers using Python? So simply to design a network in Python, there are different packages such as TensorFlow and PyTorch, and during learning CNNs, we will deal with TensorFlow package. So to install TensorFlow accurately on your device, you need to go to TensorFlow website, the installation manual, and follow the different steps depending if you are working on a CPU or GPU device, and then install the TensorFlow package. And it's highly recommended that you need to use a GPU device to be able to process the data, especially we have a good number of batches extracted from the histopathology slides. So it's recommended to use a GPU device and install the TensorFlow GPU version and ensure that the installation is done accurately. Then in TensorFlow, there is another package called Keras, which introduces a simple and abstract implementations of the different layers of the CNN, and it includes also different models and architectures for different applications such as audio handling and text handling and so on. But in our case, we are dealing with images. We will use the specific layers and functions for image from Keras. So first we imported the different functions. So you simply, by setting from something import star, you mean import all functions from that package or module. So I am here saying import all functions from the layers module and import all functions and things from the models module and so on. You can also be specific. So instead of setting star here, you can set the name of the layer. For example, as we will see, conv2d, you can write here conv2d, comma, the next layer, comma, the next layer, and so on. But if accidentally you didn't import a specific layer and you run the code will give you an error that layer is not imported, so you can import it again and rerun the code, and so on for other modules. Initially, we set the input shape to be 128 by 128 by 3, as we are dealing with RGB channels. Then we set a sequential model. A sequential model in Keras gives you the ability to build a capsulated version of a model by passing the different layers as a list. So by doing that, it will combine all of them together and produce the model object, which represents our model. In that model, we applied first a convolutional 2D layer with number of filters of 32, a kernel size or window size of 3 by 3, and a stride of 2 by 2. And we mentioned that we need the ReLU activation function and apply padding of same. And same here means you are enforcing that layer to produce a feature map which is similar in size to the input data. And for the first layer, you need to mention the input shape so that the sequential model can create an input layer with that shape. Then we applied max pooling. Then we created another cascaded convolution layer and max pooling, and a third one. But the difference here between each couple of functions, you are increasing the number of filters in each of them. So as mentioned, by increasing the number of filters, you are learning the model to extract more patterns. But this is not a general and a common rule across all of the datasets, because you can increase the number of layers and the number of filters and the performance may be reduced. So you need to tune your model if you are going to design it from abstract carefully and check if you are increasing the filters that will increase the performance or not. Then after designing the spatial information extraction or features extractions here, you are applying flattening and then fully connected layers. And we mentioned dense are also another name of fully connected layers. And for each dense layer, you are applying activation function also. So we have here 128, 64 neurons. And then because we have 3 classes, as an example, for the BACH dataset, we set here 3 neurons, but with an activation function called softmax. So the activation function named softmax here is designed to be added for the output fully connected function or layer, Because softmax function will give a probability for each class. So if you have 3 classes, it will give probability for each class, for each sample. For example, it can say that instance is benign with 0.9 and carcinoma invasive with 0.1 and carcinoma in situ with 0. So the total for each instance will be 1. So based on that, we will get the highest probability, which is benign, so the target class will be benign. For multi-class classification, it's recommended to use softmax function. And for binary classification, where we are dealing with only 2 classes, it's recommended to use the sigmoid function. Then, when you use model.summary, or whatever you are naming here as an object for your model, but you added a function called summary, summary here will print the design of your network. So you can double check that your model is correct, the input is correct, the output is correct, the cascades are correct, and so on. After that, you have to do 2 steps. The first step is to compile your model with the hyperparameters, and then you need to train your model. The training of the model will be covered in the following lecture, while the compilation will be illustrated here. When you compile your model, you are passing hyperparameters, such as optimizer. Which optimizer are you going to use? In this case, I am going to use Adam. There are different optimizers that are available in this module, which is called optimizers. And then you need to pass loss function, which loss should be used. There are many loss functions, and it depends on the problem. If you are targeting classification, if you are targeting regression, and if you are targeting segmentation, and so on. For example, one of these loss functions is the categorical cross entropy. Another one is sparse categorical cross entropy. Then you need to pass the metrics. These are the performance metrics, or the measures that judge your system is getting high performance or not. For example, there is categorical accuracy, there is precision, there is recall, there is area under curve. There are also 4 things which are related to the confusion matrix: true positive, true negative, false positive, false negative, and so on. And we will cover the meaning of each performance matrix when we perform training, so we can get a set of numbers and we judge the system performance, if it's correct, if it's high performance, if there is an overfitting or underfitting, and so on. So in summary, you are importing a set of modules, then you design your network. You can get a design and implement it, or design a network from scratch by thinking what layers should be cascaded, and by try and error you can modify your network. You can optionally print the summary, and then you need to compile your model with a set of hyperparameters, and then the next step should be the training, evaluation, and testing. And if you are satisfied with the performance metrics reported based on the dataset you are using, then you are done with the task or the design, and you're okay with that. So when we execute the code by using model.summary or the summary function, it should print something that looks like what's appearing here. We have an input shape of 128 by 128 by 3, and then we applied a conv layer with a kernel size of 3. So if you are applying our equation to get the width and the height, to check if these numbers are correct or not, so it will be 128 minus 3 plus 2 multiplied by the padding, which is 1, divided by 2, which is a stride. We then floor that number and add 1. 128 minus 3 plus 2 will give 127, divided by 2 will give 63.5, floored will be 63, plus 1 will give 64. So the width and the height will be 64. What about the number of channels? The number of channels, which is the last layer, will be equal to the number of filters. So we have in this layer 32 filters, so the number of channels here will be 32. Imagine that we have a volume like that. The shape of each of them is 64 by 64, and we have a width of 32, and this means we have 32 feature maps where each filter map is 64 by 64, and each feature map will capture a set of patterns or features according to the learning process. So you can use the formula for the width and the height to calculate the different dimension for the width and the height in the output shape, and the number of channels, which is the last layer in this case, is the number of filters applied to that layer. Then you can notice that the conv layer have a set of learnable parameters, which in that case 896. But when you reach the max pooling function, you will find there is no learnable parameters in that layer, because as mentioned, max pooling is just down samples and keeps the most important features from the previous feature map, but there are no learnable parameters or weights in that layer. So you'll find for each max pooling there are no learnable parameters. Also for the flatten there are no learnable parameters, because we are just converting from an n volume or n dimension to a one-dimensional vector. Then we have fully connected layers, and the last layer is considered the output layer with 3 neurons, each represents a category or a class. Then we have the number of total parameters and the number of trainable parameters and the number of non-trainable parameters. So in that case we have only 0 here, and as mentioned we can freeze some layers to be non-trainable. However, they will contain parameters, but they will not be trained during the learning process. Is commonly used in transfer learning on fine-tuning, and in that case you will find that number instead of 0, it will be the number of parameters which is freezed. To calculate the number of parameters for each layer or learnable layer, because non-learnable layers will be zeros as we saw, simply you will multiply the kernel width multiplied by the kernel height multiplied by the number of channels which is in the input plus 1, and then you calculate that and multiply it by the number of channels in the output. So simply we have for the first layer a kernel size of 3 by 3, and the number of channels as an input will be 3 because we were dealing with RGB, and the number of channels for the output will be the number of filters, which is 32. So by calculating 3 multiplied by 3 multiplied by 3 plus 1 multiplied by 32 will get that number. And for that layer we simply multiply 3 by 3, because in that layer also we will have a kernel of 3 by 3, and we have in that layer 64 filters. So the calculation will be 3 by 3 multiplied by the channels n, which comes from the previous layer, which is 32, then plus 1, and then we calculate that and multiply it by 64. And the same for that layer, which will be 3 by 3 multiplied by the number of channels, which is 64, then we sum 1, and then we multiply it by the number of channels in the out, which is 128, which will get that number. And to calculate the same but for the fully connected layers, for example that layer, we simply multiply the neurons from the input layer, which comes from the previous layer, plus 1 multiplied by the neurons in the output layer, which is in this layer. So we have 512 plus 1, which is 513, multiplied by 128 will give that number. And for the last layer, which is the output layer, 64 plus 1 multiplied by 3 will get 195. So now we understand how the output shape is calculated, how can we get the number of parameters for the CNN and for the fully connected layers, and to get the total number of parameters we sum all of the values in that column, and if we freeze some of the layers, we subtract the number of parameters in that freezed layers, so we get the number of trainable parameters and the number of non-trainable parameters.